In this module, we're going to look at diffraction from a point source, so a light point source. And so we can think of the image in the microscope that we're looking at, as a point object, and then kind of putting all those together. And so we want to look at diffraction because that's what's going to give us the image. And so the way that this looks, the actual diffraction of a point is going to show up as what we call this, or what you can see here in the image. This is our diffraction from a point source. This is what it's going to actually look like. We're going to have a spike in intensity in the middle, what we call the airy disk. This is what we would call, this is a bright central spot. This is diffracted light intensity, and it's what we call 0th order diffraction. So this is 0th order diffraction spot. It's the central spot. So this is just kind of a side view of that airy disk, and this is where the maximum intensity comes. Away from the airy disk, we have these what looks like little ripples, and the intensity is much lower. And these ripples are at specific distances away from the airy disk, and you can kind of see it's based on the wavelength and so forth. So these rings are first, second, and so forth order diffraction rings. And so that's what's produced when we have diffraction of a point source, which is what we have in light microscopy. So the idea here is that when we focus an image, we want to have the intensity of the light such that in between 2 points, right? If we're looking at an ideal system where we have 2 points, so we have this point and then another point, what we want to do is we want to focus it so the intensity is bright here, and then at a minimum between the rings, so between these rings here, right? That will allow us to focus and to image the 2 dots, right? So the problem here with resolution is you can boil it down to its simplest form of looking at 2 dots. And so that's what we're trying to do here. And the way to do that is to focus such that the intensity between these rings is 0. And we'll see that here in a second. Just a couple other notes about this. We can't fully eliminate these rings, so that might be your first question. But no, these rings are always going to be there. We can't fully eliminate. We can just kind of hope to minimize the intensity between the rings. So this kind of gives us that limitation. And also the central disk here, the airy disk that we're seeing, accounts for 84% of the light. So this is a majority of the light. It's a very small component. But again, like you can kind of see here, the size of this airy disk that we're looking at is going to be related to the wavelength and also the aperture of the lens itself. And we'll get more into this when we look at the specifics of a light microscope and the instrumentation that we have. And so we often look at what's called a numerical aperture. All right, I mentioned that this airy disk that we're talking about is related to aperture angle. And in turn, if you're looking at a microscope and you're looking at the lens, a way that you can measure this angle is actually through what we call the numerical aperture. This is a quantity that you can readily find, the numerical aperture, sometimes denoted NA. This is something that we can find readily available for all lenses. And so this numerical aperture includes the aperture angle within it. It includes that term. So basically it accounts for the angle theta that we have here. So it has this term sine theta within it. And so when we start talking about this, we'll be able to look at that. So when we start looking at the resolution, the best we can do, then we want to look at the radius of the diffraction spot. And so we're going to call this R. So we can define the radius of this diffraction spot related to this airy disk that we just talked about, the way that it appears, as related to the wavelength, lambda, over mu sine, and I'm going to switch and call it alpha here. So this is the aperture angle. This is the more commonly used designation for aperture angle. So this can also be rewritten as 2 times NA. So again, NA is the aperture. So effectively, we have sort of a conversion here. I apologize. So I'm going to redo this. So the first expression is related to the wavelength and also the numerical aperture, so 2 times the numerical aperture. And then we can rewrite it as mu times sine alpha, which is our aperture angle. So the factor of 2 is where you get the difference between the 1.22 and the 0.61 here. So this just kind of gives us what the numerical aperture actually stands for. But really, so far I've only talked about the aperture angle. And so this is that spread of the light from the lens, just like it was the spread of the light from the aperture. All right, so that's what we're talking about here. All right, so the main thing I want you to sort of take away from this expression, we'll come back to this in other ways, but the first thing I want you to take away from this is that our spot size, so our radius, decreases by using shorter wavelengths, but also or by looking at larger numerical apertures. So those are the two ways that we can kind of adjust the spot size. So we can reduce the spot size, which we tend to think of as better resolution, by using shorter wavelengths or larger numerical apertures. So our spatial resolution of the microscope is going to be limited to the smallest disk that's possible under these different conditions. And so, like I mentioned before, how we're going to kind of view this is not by looking at one spot on its own, but by looking at how we can differentiate between 2 spots that are close together. And so that's what we're going to do in this next part. All right, now we're, like I mentioned, we're going to look at multiple diffraction spots so that we can try to resolve them. And there are different criteria for how we resolve these spots. So I'm going to show you a couple here. The first one is called the so-called Rayleigh criterion. So I've drawn 2 spots. So this is the image that you would see. The bright part here corresponds to the bright intensity of what you see here on the graph of distance versus intensity. And then the same bright spot And then the lighter areas around it, the gray areas, correspond to those larger order diffraction rings. So with the Rayleigh criterion, we're looking at overlap, and what happens is they are just overlapping. So you can see the airy disk, and then the minimum of that airy disk overlaps with the minimum there overlaps with the maximum of the other spot. So that we have, and so the same thing. So maximum of one airy disk to the minimum of the other. And so that gives us, if we combine these two spots, it gives us a decrease in intensity between the two spots. And so we can resolve that as the gray region here. Right? So that's the Rayleigh criterion. That's where we have, we still have some intensity in between these two spots. So that's one criterion. Another possible criterion we can use, and I don't necessarily have a name for this one, but this one's slightly different. So we have two spots, but if you can, and this is what you might see on the screen or in the eyepiece, you notice that it's a little fuzzy, but if you notice here, you can see a much darker region here. And so this is a more, this is the two parts being further apart, so it doesn't give us this as good of a resolution, but it gives us better, lower intensity, right? So if we think about the addition of these two spots, it gives us lower intensity here. And this happens when we think about these two spots, the minimum between the airy disk and the first ring corresponds to the other minimum of the airy disk and the minimum ring for the other spot. And so this is where we have a very minimal intensity. So ideally, we could have zero intensity between these. So we should be able to really resolve these two spots. So this is kind of an overly, maybe potentially overly engineered system where we don't necessarily need that fully minimized here. And so we could go to the Rayleigh criterion where, we don't have minimum intensity, but we're still able to discern the drop here, the minimum as opposed to the maximum of each spot. So that's just kind of a difference of designations. But this, this kind of foundation, either this or the other one, would allow us to determine what our best possible resolution is given our numerical aperture and our wavelength. And so that's what we're going to do in the next module.